1 year ago, I wrote the first lines of code of one of the most rewarding but challenging projects I've ever worked on. Recreating Gen 3 Pokemon using 100% JavaScript and no frameworks and no external libraries. A year later, and the project looks and feels amazing. It features most of Gen 3 mechanics and it feels almost like the real thing. The project still has a long way to go, but it's mature enough so that the way it works under the hood is going to remain largely the same as development goes on. And I'm super excited to put together devlogs and progress updates for you guys. But I wanted to give you the technical context of the whole project in this one video so that future videos make a little bit more sense. So today I'm going to give you guys a high-level overview of how the entire project works and how I made it using only JavaScript and a few tiny lines of Python. And don't worry, coding experience is not required to enjoy this video. I'm going to go ahead and explain everything in a way that people of all ages and all experience levels can enjoy. If anything's unclear though, please let me know in the comments and I'm going to respond 100% guaranteed. So let's get started. But first question is, where the hell do I even start? I took a step back and I thought to myself, okay, what are the most basic things that I need to accomplish in order to get this game going? First thing is I have to draw something on the screen. After that, I gotta figure out, okay, how can I draw things on a screen multiple times in a second? Ideally like 60 times a second. And third, how do I control the things that are on screen in between every render? So let's answer these one by one. So we wanna draw stuff on screen. And as we know, our screen in this case is just going to be our web browser window. It could be Safari, Firefox, whatever you want to use. And since December 2017 was over 7 years ago, yikes, we have access to a thing called HTML5 and most importantly, HTML Canvas. As you can probably tell by the name, Canvas is the thing that we're going to use to draw stuff on screen. It has a super simple but very, very capable API that I was able to get to grips with even though I had zero experience with it whatsoever. Drawing things with it is extremely simple. So we now know how to draw things on screen, but how do we draw things multiple times per second? For this, I went with window.requestAnimationFrame. The way it works is that you give this method a function or a block of code, and the web browser is going to try and run this code every single time it renders a frame. So we take our drawing code from earlier, we pass it on to requestAnimationFrame, and bam, we're drawing things basically 60 times per second or whatever the refresh rate is for your current device. With these two key points alone, you probably have enough information on how to answer that third question. How do we control the things that we're drawing in between each frame? Well, the short answer is we can pass requestAnimationFrame some more code that controls the properties of the things that we're trying to draw, such as position, size, visibility, etc. For example, if we increase a sprite's X position by 1 in between every single frame, when you run the whole thing, it's going to appear like the sprite is moving from left to right at a rate of 1 pixel per frame, so 60 pixels per second. If we zoom out conceptually back enough, you can see that this is pretty much all that's happening in a game. A game is just a huge chunk of data and logic that controls the way things are displayed on screen and listens to user input. It's way easier said than done though. One thing is writing a script that moves the sprite from left to right, but how do we expand this whole thing into an entire video game? Whenever you're developing any piece of software, you want to make sure that you separate the code that renders things on screen versus the code that actually takes care of all the game logic or the business logic. So for this game, and in service of that, I created these two entities, the graphical user interface or the GUI, as well as the state machine. The GUI is going to handle rendering all the sprites and all the visual things on screen, and the state machine is going to take care of all the game logic. Let me give you an example of how these two entities interplay with each other. So again, let's go back to the example of the sprite that we were moving from left to right. The state machine is going to take care of figuring out what the position of the sprite should be. Once the state machine decides where the sprite needs to be drawn, it goes to the GUI and says, hey GUI, you should go and draw the sprite in this position. And the GUI is going to be like, all right, bet, let's do it. And the GUI draws the sprite accordingly. And so this conversation in between the GUI and the state machine is going to be happening in between every single frame. So between 60 and 120 times per second, of course, depending on your screen's capabilities. Let's peel the onion back on both the GUI and the state machine. Let's really try and see a little bit more about how these are working under the hood. Let's talk about the state machine first. So what even is a state machine? The best way I could explain it, it's kind of like this flowchart that just keeps track of all the different situations or states that your game can be in. The cool thing about this design pattern is that it really allows you to organize huge chunks of logic and code into a much more manageable way. You might end up writing a bit more code than maybe with other approaches, but it really keeps you sane. To get a state machine started, you really only need 3 things. A list of all the states that your game can be in. Second, what triggers a state change in between each of those states. And 3, and most importantly, what happens when we're actually in each state. So let's answer these 3 questions using our previous example. Let's say we only have 2 states, okay? We only have idle and moving. So we decided all the states that we need. Secondly, how do we transition between states? So we transition from idle to moving whenever the player presses the left or right D-pad button. And we transition from moving to idle whenever the player releases those buttons. So we have our 2 states, we have our transition condition, and so now we have to define what happens. So in our idle state, nothing happens. The player just chills there. But in our moving state, the player's position changes depending on what button they pressed. It might sound like this is all like just a fancy if-else chain, and in reality, under the hood, this whole project is powered by a huge switch statement, so you're not that off. But I found that using this design pattern helped me organize the project in a way that kept me sane. Okay, so we know how the state machine works. Let's now look at the GUI. The explanation here is way simpler than for the state machine. As I said earlier, the GUI decides what to draw and when, and it makes these decisions based on what the state machine has to say. The GUI also has the immense responsibility of deciding the draw order of things. Let's take a look at this tree, for example. As a player, I should be able to walk behind the tree in this case, and the GUI makes that possible by drawing the tree after it draws the player. Otherwise, we'd run into this situation. So before we go any deeper, let's take a quick step back and just recap what we've talked about, just to make sure you guys are still with me. First, we're using HTML canvas to draw things on screen. Then we're using window.requestAnimationFrame to draw things on screen multiple times per second. And on each frame, the state machine is going to perform calculations deciding what needs to be drawn and when. And the GUI takes a look at the state machine and says, okay, these are the things that I need to draw, and this is the order in which I need to draw these things. A simplified version of the code currently running in my game looks something like this. On each frame, we have our state machine and our GUI running their own update methods. These 2 methods seem to be doing a lot of the heavy lifting, so let's dive into them a little bit and see how they work. So, like I said earlier, we know that our state machine is in one of several dozen states. But what's happening in each state? Like, what's really happening in the code? So the way I designed this, each state executes a list of actions, and each of these actions needs to be executed in order. Every time the state machine executes one of these actions, it discards it from this list of actions. When the state machine runs out of actions to perform, it asks itself, okay, do I want to retry this state and this whole list of actions again? Or do I want to move to a different state and perform a whole different list of actions? And depending on a whole list of criteria, depending on each state, it makes that decision. So what does that look like in the code? This here is the exact implementation of the update method of the state machine running in my game. I encourage you to pause the video here and check it out for yourself, but please let me know in the comments if there's anything here that's unclear or that you would like a bit more explanation on. Now that I've explained how the game works under the hood, I feel a little bit more confident in putting out some more devlog videos, kind of explaining a little bit more in detail how future updates work. And trust me, I have a lot of updates that I want to share with you. Some of these include an updated Pokédex, overworld HM usage, diagonal movement, the list goes on. I've been overjoyed at the support I've received in my past video and in my shorts. So I really appreciate you guys just chiming into the comments and clicking that like button. It's been 100% positive energy all around, and it's really motivated me to kind of keep going with these videos and keep going with the project. Thanks so much for sticking around all the way to the end. Stay cozy, and I'll see you on the next one.